So today's lecture is about some basics of software engineering and how it comes along in Haskell. So I'm going to cover a whole bunch of concepts here. I will do this mainly by means of live programming, but you are welcome to go through all these concepts yourself, one by one. Um, so just a reminder, what is software engineering? Here's a simple definition. It's the application of a systematic, disciplined, quantifiable approach to the design, development, operation, and maintenance of software. And the study of these approaches, that is the application of engineering to software. So we really just will cover here the basics of software engineering in the sense that we exercise some aspects such as modularity, or local scope to better structure the program. And then also we will exercise build management to kind of combine compilation, testing, and packaging. Indeed, we will look a little bit deeper into testing and also into proper documentation. To this end, we will use certain kinds of tools. A build tool, a package management system, a testing framework, a documentation generator, and in fact, we will use the Haskell counterparts for these categories of technologies. We will go through a bunch of sample contributions of our lovely 101 system, and in this manner we will exercise these software engineering concepts. So let's maybe jump to coding right away. So here we are in the Haskell starter directory, which by the way is also linked down here. So if you go here, you can get the code, like all the code as you probably know by now, from GitHub. So we are on this directory. Here's the code. And now let's modularize this code. So what is modularity? Modularity is basically that you break up your solution into units, so-called modules, that have some well-defined purpose, some interface, so that other modules, programs can reuse those modules. So if you look at this solution here, and you have seen this before in the introduction to this course, this is the very simple solution which has this sample company here with some employees, and we then have functions to compute the total overall salaries, and here we also have a cut function to halve all the salaries, and here we have a main function. And just to show you, just to remind you how this all feels like, let's just we are not in the right directory. This is in the source directory. So let's just load this program. Let's just run the main function. So the first result here is the total of the salaries. The second one is the cut salary. Now, and if you look around here, this is just the entire code that we have here in the editor. And now let's split it up into some units. So for no reason, maybe let's start here. So this is the sample data. Let's just cut it out, and let's just put it into, let's just create a company directory, and let's put it into, let's call it sample AJS. Okay, so this would be the sample data, but actually we already see it's using stuff from what should be another module. But anyway, let's first give a name to this. Let's say this is module company sample, and this is what's in the module. Now, what we actually need is we need these kind of type definitions here. So let's already imagine we have such a module. Let's call it company data. Okay, so we go here. In fact, this code seems to correspond to the data model that we use in this example. So let's indeed create a module data HS. Let's put it there, and let's also give a name to this module here. Okay. So now we already have two modules, namely the data model and the sample data. And just to show you that this already somewhat works, we can already load, let's say, the sample module. So you see we are loading the sample module, but as part of its import, it also imports the data module. Okay, so we have two modules here. And now let's split up this some more. I mean, we could either have a module just for total and another one for cut, but let's just go fast here. Let's just create a module where we have both in there. Let's just call this functions. And so these are the functions. So we call this company functions. And as you can already see, just by looking at the function signatures, we obviously should also import here company data, because the data types, company, float, etc. Well, float is predefined, but company and salary and employee, we need them here, so we better import them. And now we are back to here. So there's nothing left here. Well, we have to import everything here. We want to apply actually the functions to the sample. Well, we don't need to import company data here because there's no direct reference. So let's just comment it out. So we don't need it here. Likewise, here in the functions, we don't need to import the sample because these are just functions and we're testing them in the main module. And this is why it suffices to import the sample here. Now we can go back here and load main again. So you see it now loads all the involved modules that we just created. And if we run the main function, we still get the same result. So the only difference really is that we now have a more modular solution, and we have, through the import clauses here, we also have defined very well what we need in what scope. Okay, so this brings us back to our main page here. So we have covered some basics of modularity. Another issue that's sort of related, and it's also about better code organization, is the issue of scope. So we already generally interact with the notion, the more general notion of scope, in the sense that by using these import statements, we bring into scope certain kinds of declarations. Here and here we actually don't import anything, and here we import something specific, and also here we import something specific. So this is already about scoping, right? So a module also provides a scope, and by importing declarations from other modules, we do bring things into scope. Now, on top of this, there is also in many programming languages something what you might want to call local scope. To understand this, look at this situation here. We have all these functions, and they are all defined at the top level. But this is actually somewhat misleading. So if someone looks at this module, then that person might say, actually, why do I need to bother about all these functions? Are they all relevant for me? So we could do two things. Either we could go here and explicitly say we only possibly export from this module these two functions, and all the others are just local functions. But then, I might still look at this declaration and forget about the top level line here, and I might still be confused. Are these actually important functions or are they helper functions? And so what we do instead is we actually bring some of these functions into local scope. So this is how we do it in Haskell. We basically start a where clause and we indent these functions so that they get here into the scope of total. And now if you think of it, actually the get salary function is only needed here. So if you want to be very precise about the relevant scopes here, we can actually even indent more and put get salary under the scope of get salaries. Now we could do something similar here with the cut functions, but I omit this. And just to convince you that this still works, if I haven't done any mistake, well, obviously I have done a mistake. Yes, so I haven't indented enough. So I need to indent some more here. So as you know, Haskell is all kind of indentation dependent. Other than that, everything still works. So I have done a better job in explaining what function, especially these helper function, are needed in what scope for what part of the program. You can look at a different example here online, and there's also explained how scope is relevant in other programming languages. You're welcome to look at this in more detail. So this should suffice for now for dealing with modularity and for scoping out things, and for bringing things into scope, to import. So let's move on to build management. I think in the introduction we have talked a little bit about compilation and interpretation, and as you know also from other languages, compilation is meant to somehow translate a program in a more efficient representation, some sort of machine language, so that it can be executed very efficiently. What we have used here is actually an interpreter, but actually what you see what happens here on the fly, some sort of compilation happens anyway. Now, when you really want to create a software product, some sort of package, some sort of release, what you typically use, and many of you know this, of course, you use some sort of build management. And let me show you how this feels like in Haskell. I mean, there's different ways of doing this in Haskell. So we are now in a different directory here. We are in the contribution Haskell engineer directory. And what we have here is we have a kind of a build file. This is the Haskell engineer Cabal file based on the Cabal technology for Haskell, which is sort of a build management system. Underneath it, there's also a package management system. So I have documented the steps to build a release, to build a package for this contribution as makefile. So even if you don't use makefile, so makefiles don't play any essential role here. It's like a README, how I'm using it. So just to remind myself, so basically when we use the build tool, Cabal, what we would do is we would run these steps in order to completely build a compiled version and check all the dependencies that we have. And you see, and we will get into this a bit more in detail very soon, also to test the package. So I could now either just copy this and into the console, or I just use make build, and this will run all these steps. So what happens is that actually Cabal checks on all the files that I say belong to this package. It also checks all the dependencies that I say I need to build this package. In this case, for example, I rely on a test tool. And then what you see here, it also runs a test suite. So we were cleaning some stuff, we were configuring it, in a certain way because we want to run tests eventually. We build the package and we test it. And if you look around here, we now suddenly have this new directory here, this new style. Okay, there's a build directory, build, there's something in here, base for something built for this particular version, and here we have the package that we just built, and in there we have the build, and now what you see here is actually compiled code. So there's the compiled main module. Okay, so this is how it feels like to actually build a package or to make a sort of release in this context. Let's go back all the way up here. Now let me show you this Cabal file. It's this one. So this is basically a domain-specific language just to describe the all the ingredients for building a package. So we've got a name, we've got a version, a short explanation. We also point to a place, in this case on a wiki, where more information can be found. We assign some sort of build type. We also say with what version of the build tool we want to build this. And then we expose some modules here, and you see we went for very similar modularization than the one I explained earlier. So these are the modules like main, data sample, total cut. And here are some interesting dependencies, and we will get into testing in a second. So, well, we depend on some base library, but we also depend on what's called HUnit. This is a testing library. And so this is how we actually essentially compile the library for this contribution. And here in the last few lines, we describe how we actually test this package. And apparently there's some testing code in main in here. And again, we express our dependency on HUnit. And we also describe the kind of testing that we perform here. So in this case, apparently we rely on some sort of exit code based mechanism in order to communicate whether testing was successful or not. There's other ways of doing this. Yeah, so this is, so we can also run make test here again. Well, Cabal test, sorry. So we run the tests again, and you see we passed some test suites. So this is then a good time to look a bit more into testing. So let's click testing here just to have some very extensive explanation of what testing is. Well, as usual, you might be well advised to read up somewhere else if you don't find enough information here. So the particular kind of testing that we perform here, and I think some of you, many of you may have exercised unit testing for other languages, is that we, yes, perform unit testing. And what is a unit in Haskell? Well, typically a function. So we typically test a function. Okay, so let's actually look at, we will also go back to live programming in a second. But just to remind you, there's also extensive documentation on the wiki. Here's the Cabal part that we just looked into. Here is the scoping part that we also just looked into. The external dependencies are explained here. Now, here is the testing related stuff. So we have a certain number of test cases in order to, in this case, test that total works as expected, that cut works as expected, and also that we can, what we call serialize or read and show in Haskell, the sample data. So let's switch to the code here. So we go to my Git directory, to 101 Haskell, contributions, Haskell engineering, source. In the main file, we have all these tests. So this is the organization of the main file. And you see we actually import the testing framework here, HUnit, Haskell unit. We also import system exit. This is how we communicate success and failure of tests to the outside. And now let's look in more detail at the tests. And maybe just to remind you, the main function now is solely focused on running tests, whereas if I just briefly switch back to what we had before, here the main function was not really testing, it was merely printing some numbers. So what we do here is we run the tests as defined here, and then the idea is that these tests, as they are executed with this framework function, they return certain counts, namely error counts, success counts, failure counts. And what we do here is if there's an error count or failure count, then we exit with failure, otherwise we exit with success. And the difference between error and failure has to do whether we throw an exception, whereas those get a result that we didn't expect. So now let's look at the individual cases here, the individual test cases. And they are structured pretty much in the same way. They use this weird, special kind of equality operator. And this is done in this way so that the test framework can keep track of the test case execution. So we essentially compare the result of applying total to the sample company with this expected result. And so the test case goes fine if, well, this equality holds, otherwise we have an error. Or if something really bad happens, we have a failure. Or was it the other way around? I forgot the terminology. So let's look at the next test case. So this is how we test cut as opposed to total. What we do here is we actually invoke cut on a sample company, and then we compute a total thereof. And then the expected result, we don't just hard code a specific float here. We simply divide the total for the sample company before cutting the salaries. We divide it by 2, and that should be the same as totaling all the individual salaries after cutting them. Of course, this is a little bit dangerous. We might need to use an epsilon here in general because, well, we're dealing with floats, but it appears to work here. And here's the third test case. It's about testing what we call serialization sometimes, or in Haskell, read and show. So here, when we are in the session for one of the contributions and we say show, we turn the sample company, which by the way looks like this. We turn it into a string. You see it's now a string. And by the way, when you enter a sample company at a prompt, what happens underneath is that it also shows the text, in this case just without the double quotes. So this test case, what it tests is if we show the sample company and then read back in the string into a company, then of course we should get back the original company. Otherwise something would be lost on the way in and out. Okay, so this is how we perform simple testing. And somewhere else, but not today, we will look into other forms of testing. So the basic idea is that you can test functions such as total, cut, read, show. When considering them as units, you test them by such cases, and specifically you test for quality with some expected result. Okay, let's go back to the web page. we are nearly done here. So one more topic I want to briefly discuss is documentation. I mean, this is obviously also part of basic software engineering practices, that you document properly your code, not just test it, not just build it, type check it, compile it, modularize it. So where are we here? We are in Starter. Now let's go here to Haskell Engineer. And let's just remind ourselves of all the good things we can do with Cabal. And here's one thing, Cabal head doc. So basically head doc is the documentation generation tool for Haskell, and Cabal just helps us invoking it here in some controlled fashion. So what we do is we ask Cabal to apply head doc to all the modules that are part of this package. And the assumption is that all these modules are encoded in a certain way to appeal to certain documentation idioms. And then what we get here is we get some web-enabled documentation. So we are told that this is the documentation that was generated. We can look at it. This is it. And you see we now have like a nice documentation for our package. And for example, we can go to, let's say, company total. And you see we only see the interface here of the module that maybe is useful for others who want to use this package. And of course, there's some minimal documentation here for each function. And there's also some minimal documentation here at the top of the module. And the way that we are kind of instructing HeadDoc to generate that sort of documentation is that we use certain idioms that I'm going to show you. So you see, we use special Haskell comment patterns here, in particular this open brace minus bar, and this instructs the documentation generator that this is the top level, this is the module level documentation, and then at the level of the individual functions, we can also use this sort of comment here, Haskell comment sign space bar, and this means use this comment when generating documentation. If we were somewhere here adding other comments, those would not go into the generated documentation. This is one particular style of dealing with documentation, but as you can see, it complies very well with modular programming as we were discussing it in the beginning. So I think this might be all the topics that I wanted to discuss here today. So that's it. Thank you.